Welcome to our second lecture in the fourth week of our course Analysis of a Complex Kind. Today we'll learn about conformal mappings. What is a conformal mapping? Intuitively, it's simply a mapping that preserves angles between curves. What I mean by that is the following. Look at these two curves, gamma 1, and let's give it an orientation, and gamma 2. They intersect at this point that I drew right here, and if you look from this point in the direction of gamma 1 and then look over to where gamma 2 is, that gives an orientation to the angle between those two curves. That's the angle between the curves I'm talking about. Now let's imagine a function f maps this picture to a separate picture. So here's f of gamma 1, and here's f of gamma 2, and again, if I stand at the point of intersection and look from f of gamma 1 to f of gamma 2, I get another oriented angle. If these two angles are the same, then we say the mapping f preserved that angle. So conformal mapping is a mapping that preserves all angles between all curves you could possibly draw. In order to make this precise, we're going to have to define exactly what we mean by a curve, and also what we mean by the angle between curves. How exactly do you measure an angle between curvy segments? That's what we're going to do right now. Let's start with the notion of a path. A path in the complex plane from a point A to a point B is a continuous function gamma that lives in an interval. This is an interval on the real line. So, an interval from A to B. So a continuous function from this interval into the complex plane, such that gamma of A is A, and gamma of B is B. It's a continuous function, and so between A and B, you'll find the image of this interval as some kind of continuous, non-interrupted path. So here I drew a point gamma of t, for example. Let's look at some examples. Gamma of t is the function 2 plus I plus e to the it for t between 0 and pi. What does that look like? Let me draw some axes. Let's try to figure this out. E to the it, we know, describes a circle of radius 1 if t runs from 0 to 2 pi. Now we're running from 0 to pi, so it's going to be a half a circle. But we're also shifting that circle because we're adding 2 plus I to all those numbers. 2 plus I is, say, right here. And now we're adding e to the it to that. So this is going to be a curve like this. I have a circle centered at 2 plus I. So this is our function gamma of t. This is the point gamma of 0. And this is the point gamma of pi. So in our definition up here, a is 0, b is pi, and gamma of t is this function that you see down here. We could break this function up into its real part, x of t, and its imaginary part, y of t, by breaking up e to the it as cosine t plus I sine t. So just like we did for a complex valued function of a complex variable, we can break up this complex valued function of a real variable into its real part and imaginary part. The only difference is that t is a real variable here, and not a complex variable. And that's why we get a path versus something two-dimensional as the image. Let's look at another example. Gamma of t equals 2 plus I plus t times minus 3 minus 5i, and this time t goes from 0 to 1, so a is 0 and b is 1. Let's first of all find out from where to where in the complex plane this path works. When t is equal to 0, gamma of 0 equals 2 plus I plus nothing, so just 2 plus I. In other words, this path starts at 2 plus I. This is my point gamma of 0. Where does it end? Well, it ends at gamma of 1. What is gamma of 1? That's 2 plus I plus 1 times minus 3 minus 5i. And that is equal to 2 minus 3, which is minus 1, plus I times 1 minus 5, so minus 4. So minus 1 minus 4i. That is somewhere down here. What does the path do in between? It keeps subtracting more and more from gamma of 0. It is a linear mapping from gamma of 0 to gamma of 1. And again, we could break this up into the real part and the imaginary part if we wanted to. Here's another example. Gamma of t equals t times e to the it. Again, let's try to draw this. This time, we're letting t run from 0 to 3 pi. Gamma of 0, or 0 times whatever is equal to 0. Gamma of 3 pi is equal to 3 pi times e to the I times 3 pi. But e to the I times 3 pi is the same as e to the I pi, because the function e to the I something is periodic with period 2 pi. But e to the I pi is negative 1, so that is minus 3 pi. So this starts at 0, and it ends somewhere way out here at minus 3 pi. When t is equal to pi over 2, normally that would be at the 90-degree turning point of the circle, the value is e to the I pi over 2, which is I times pi over 2. So we're going to be right here. So the curve does something like this. It's like a circle, but instead of being a circle of radius 1, the radius keeps increasing. What does it do from there to pi? From here, the radius keeps growing to pi. 2 pi. It's not a good picture, but you get the idea. It's a bad picture, really. You can do much better than that. But this is a spiral. This curve spirals from a radius of 0, and the radius keeps increasing, and the curve keeps going around and around and around. Here's another example. Gamma of t is defined in 3 different ways, depending on whether t is between 0 and 1, between 1 and 2, or between 2 and 3. Let's try to draw this curve as well. For t between 0 and 1, we're looking at the function t times 1 plus I. When t is equal to 0, that's just 0. When t is equal to 1, we're at 1 plus I, which is, say, here. If this is 1, and this is I. So from 0 to 1, that's what the curve does. Next, between 1 and 2, we're looking at t plus I. In other words, the real part changes from 1 to 2, but the imaginary part stays fixed at 1. So in other words, this is what happens. The imaginary part stays fixed, and the real part increases from 1 to 2. Between 2 and 3, we're looking at 2 plus I times 3 minus t. So now the real part remains fixed, and the imaginary part changes. And it starts with t equals 2, and 3 minus 2 is 1 at I, so it starts right here, and decreases from there to 0. In other words, this is what the curve does. So altogether, this is my curve gamma of t. We say that the path is smooth if these functions x of t and y of t that make up gamma of t, so if you split up gamma of t into its real part x of t and its imaginary y of t, if these two functions are smooth. And by that we mean that they have as many derivatives as we need to. Let me quickly remind you of the example that we just looked at. Example number 1 was this semicircle. Example number 2 was the straight line segment. Example number 3 was our spiral. And example number 4 was this path that was put together from line segments, like this. So in these examples, this first one is nice and smooth. You could have found the derivatives, in fact, of x of t and y of t. The next one is just as nice and smooth. This one is just as nice and smooth. But this one has some corners, and the derivatives, these functions x of t and y of t, would have a hard time existing at these corners. So 1, 2, and 3 are smooth, whereas 4 is called piecewise smooth, because away from the corners, everything's good, but at the corners, the derivatives don't exist. So this is called piecewise smooth, which means it's put together or concatenated from finally many smooth paths. The term curve is typically used for a smooth or a piecewise smooth path. So all these examples from above are allowable for being curves. Now, if gamma, written as x plus iy, is a smooth curve, and t0 is a point in that interval where the function gamma is defined, then we say the derivative gamma prime at t0 is x prime of t0 plus iy prime of t0, and that is a tangent vector to the curve gamma at t0. And let me demonstrate to you why that is the case. So suppose here's this curve gamma, and suppose here is gamma of t0. That's the point we're looking at. Now let's look at this derivative gamma prime of t0. What is the derivative? The derivative is obtained by looking at gamma of t0 plus h, which is maybe this point here, and looking at the difference gamma of t0 plus h minus gamma of t0 and dividing that by h. But gamma of t0 plus h minus gamma of t0 is this vector. And we're dividing that by h, which is a real number, so that changes the length, but not the direction of this vector. As h moves closer and closer to 0, the second point moves closer and closer to the first point. Thereby, this vector becomes more and more a tangent vector. In the limit, we get the derivative, which is the tangent vector to this curve at the point gamma of t0. So the derivative represents a tangent vector to the curve at t0. Now, if you have two smooth curves, gamma 1 and gamma 2, and they intersect at a point z0, then we say the angle between these two curves is simply the angle between the two tangent vectors. So you find a tangent vector to gamma 1, you find a tangent vector to gamma 2, and you take the angle between the two of them, from gamma 1 to gamma 2. That is defined as the angle between two curves. Because we know how to find the angle between two lines, the angle between the curves is simply defined as the angle between the tangent vectors to the two curves. Let's look at an example. Suppose gamma 1 is given by gamma 1 of t is e to the it. So again, that's a circle, and we're letting t run from 0 to pi. So you get this curve right here, this curve gamma 1 right there. Gamma 2 is also of the form 2 plus I plus 2 e to the it. So it's also a circle. This circle is centered at 2 plus I, however, and its radius is 2. And we're starting at pi over 2, so we're starting at this point up here, and it runs through t equals 3 pi over 2, so all the way down here. So gamma 2 is this green curve over here. These two curves intersect at I. In fact, gamma 1 of pi over 2 is the same as gamma 2 of pi. That's where they intersect at I. Let's find the tangent vectors for these two curves. Gamma 1 prime, the derivative can be found in two ways. Either you just use the chain rule, and you get its I e to the it, or if you wanted to write gamma 1 of t in real part and imaginary part, that would be cosine t plus I sine t, and then you could find the derivatives separately. So gamma 1 prime of t would then be the derivative of cosine, which is minus sine t, plus I times the derivative of sine t, which is cosine t. If you factor out an I, you notice this cosine t is left by itself. And if you factor out an I from minus sine t, that's the same as writing plus I times sine t in these parentheses right here, because if you were to multiply this I back in there, the I squared gives you this negative sign. But cosine t plus I sine t is simply e to the it, so this is I times e to the it. Or you could have just, as I said, applied the chain rule, and the derivative of e to the it can be found as I times e to the it. Gamma 1 prime, at the point where these two curves intersect, namely pi over 2, is then I times e to the I pi over 2, but e to the I pi over 2 is another I, so we get I squared, which is negative 1. So the tangent vector to the curve gamma 1 at t equals pi over 2, or at the point I, is minus 1. I move this vector and had it start right at the point I, and it points simply in the negative direction. It has length negative 1. So that is, this vector right here is the tangent vector to the curve gamma 1 at the point I. We can do the same thing for gamma 2. Gamma 2 prime of t, 2 is a constant, I is a constant, the derivative is 0. The derivative of 2 e to the it is 2I e to the it. If you plug in pi, which is the parameter that yields the point I for gamma 2, you get gamma 2 prime is 2I e to the it. E to the it is negative 1, so you find 2I times negative 1, which is minus 2I. If I attach a vector, the vector minus 2I at this point I get this vector right here. In other words, the angle between these two curves is this angle right there. So this angle points counterclockwise, and that is what we call the angle pi over 2. The angle between those two curves equals pi over 2. Finally, we're able to really define what it means for a function to be conformal. We say a function is conformal if it preserves angles between curves. So that means precisely a smooth, complex-valued function g is conformal at a point z0 if whenever gamma 1 and gamma 2 are two curves that intersect at that point z0, so any two curves, gamma 1 and gamma 2 that intersect there with non-zero tangents, then their images under g, namely g composed of gamma 1 and g composed of gamma 2, have also non-zero tangents there and intersect at the same angle. So, suppose this is g of gamma 1 and this is g of gamma 2, the requirement would be that the angle from gamma 1 to gamma 2 is the same as the angle from g of gamma 1 to g of gamma 2 when you're standing at this intersection point. This is the point g of c0. And the angle is measured in terms of their tangents. A conformal mapping of a domain D onto some V is a continuously differentiable mapping that is conformal at each point in D and maps D 1-to-1 onto V. It is thus not enough to simply be conformal at each point in the domain D. Moreover, we require that the mapping map D in a 1-to-1 manner onto V. Then we say we're dealing with a conformal mapping. Otherwise, we can say the mapping is conformal at a point. But in order for it to be a conformal mapping, we require that it's conformal at each point, in addition to being 1-to-1 and onto V. What does all this have to do with analytic functions? Well, analytic functions kind of bring conformality with them for free under very minimal assumptions. If f is an analytic function in a set U, and c0 is a point in the set U, such that its derivative is non-zero at c0, then f is automatically conformal at that point. Analytic functions are conformal almost everywhere, except when the derivative is equal to 0. As soon as the derivative of an analytic function is non-zero, the function is conformal at that point. It preserves angles between curves. Let me show you the reason why that is true. Suppose gamma is a curve that goes through this point z0, and then what is the derivative of f of gamma? The derivative of f of gamma at t0 by the chain rule is f prime of gamma of t0 times gamma prime of t0. But f prime of gamma of t0 is just our z0. So that's f prime of z0 times gamma prime of t0. This was the tangent vector to the curve gamma at z0. This is the tangent vector to the curve f of gamma at f of c0. And how do they differ from each other? They differ by being multiplied with f prime of c0, which by assumption is a non-zero number. What does it mean to be multiplied by a complex number? Multiplying by a complex number means we're rotating and possibly stretching. So the tangent vector to the original curve maybe gets rotated and possibly stretched. But it's rotated and stretched by this number f prime of z0. So now I have two curves, gamma 1 and gamma 2, through this point z0, and with their respective tangent vectors. Then the image curves, the tangent vectors to those image curves, are also obtained from the original tangent vectors by simply rotating and stretching, with the exact same rotation and stretching. Stretching doesn't change an angle at all. Rotation is a rigid Euclidean motion, and if you rotate two vectors by the same amount, then in their image, the angle hasn't changed. The angle doesn't change by rotation. And that's why the angle is preserved under analytic functions as long as the derivative is non-zero. Let's look at some examples. Let's look at the function f of z equals z squared. Let's restrict it to the right half plane. So use this right half plane over here. If we restrict after the right half plane, it's a one-to-one function onto the whole complex plane minus the negative real axis. And furthermore, in the right half plane, the derivative of this function is 2z, which is never equal to 0 in Q. Because we're seeing away from the origin, we're requiring the real part to be actually positive. So the origin itself is not in there, which means the function is one-to-one, has a non-zero derivative, and maps it onto the whole plane minus the negative real axis. So z squared is a conformal mapping from the right half plane onto the whole plane minus the negative real axis. The function e to the z is conformal at each point in c, because its derivative is never equal to 0. F prime of z is also equal to e to the z. That's never equal to 0, no matter what you plug in, and so e to the z is conformal at each point in the complex plane. But f is not a one-to-one mapping in c because we know it is periodic with period 2 pi I. It keeps repeating. So if we look at the function on the whole complex plane, it's never going to be a conformal mapping. However, if you restrict e to the z to, for example, this strip where the imaginary part is between 0 and 2 pi, the function does not repeat in there because for any point it repeats 2 pi I later. But you can't have 2 points in the strip that are 2 pi I from each other. So if you restrict after the strip, then its derivative is still non-zero everywhere. It's one-to-one in there, and it maps that strip conformally onto its image, which happens to be the whole plane minus the positive real axis. We're not including the real axis in this domain or the line 2 pi I, which means we're not really hitting every point in the complex plane as an image. We're omitting those points that are images under f of the real line or the line 2 pi I or the line 4 pi I. So that's why it's the plane minus the positive real axis that we're mapped onto. Finally, let's look at f of z equals the complex conjugate of c. That's clearly a one-to-one onto function from c to c. However, angles between curves are reversed in orientation. Let's look at this curve gamma 1, for example, and the curve gamma 2. If you find the complex conjugates, all you have to do is you reflect this over the x-axis. That's what the conjugate really does. So the image looks something like this. Here's f of gamma 1 and there's f of gamma 2. But whereas the angle from gamma 1 to gamma 2 was counterclockwise, the angle from f of gamma 1 to f of gamma 2 goes clockwise. So even though the magnitude of the angle hasn't changed, its orientation has changed. That is not allowable for a conformal mapping, and therefore this mapping is not conformal anywhere. In the next lecture, we'll look at Mobius transformations. These are special conformal mappings with many special properties that are very exciting. We'll spend 2 lectures learning about these Mobius transformations.